Welcome to the 2018 NASA Ames Summer Series. We tend to think that we are in an era where rapid, disruptive, and innovative technologies and breakthroughs are occurring. Yet, if you think about it, airplanes started with propellers and then moved to jets. Jet engines were from the circa of the World War II era, and we're still utilizing jet engines as the most prevalent propulsion that we have for airplanes. And so also, spaceflight and space propulsion looks at the same way in terms of disruptive technologies that are needed to be developed. Today's presentation is entitled STARLIGHT, Directed Energy for Relativistic Propulsion, and it will be given by Dr. Philip Lubin. Dr. Lubin is a professor of physics at UC Santa Barbara. His primary research focus is on early universe in the millimeter wavelength bands, as well as applications of directed energy for planetary defense and relativistic propulsion. He received an AB in physics and mathematics from UC Berkeley, a master's in physics from Harvard University, and a PhD in physics from UC Berkeley. Using Antarctic and balloon-borne systems, Dr. Lubin's team was the first to detect horizon-scale fluctuations in the cosmic microwave background. His research continued in collaboration with ESA on the Planck cosmology mission, resulting in extensive structure mapping of the early universe. He is the director of the NASA STARLIGHT program, a phase 2 program studying the use of directed energy for humanity's first interstellar missions, and a concept director of the Breakthrough Starshot program, which aims to achieve relativistic flights with miniature spacecraft. He authored hundreds of publications and papers, received numerous awards, including the 2006 Gruber Prize in Cosmology and the 2018 Gruber Prize in Cosmology. Please join me in welcoming Dr. Philip Lubin.
Okay, well, thanks for coming. Appreciate you giving up your time. I will now violate the prime directive by drinking. I'm not sure what the consequences of that are, but I'm sure I'll find out. Okay, unfortunately I teach for a living, which means I am not prone to finishing early, but I'll be thrown out at the appropriate time, so I won't get through all the slides, I'll tell you that. This is a program which is truly transformational if we pull it off, and I'd like to lead you through the consequences of both pulling it off and the reasons why it's consistent with reality and not a science fiction-based technology. Again, it's funded through the NASA NIAC program, which is the Advanced Concepts Office. It's also funded by Breakthrough Initiatives, of which Dr. Warden is the director. So please talk with him. He's just an amazing person in my mind. He's very, looks way beyond the ordinary. It's also funded by the Emmett and Gladys W. Technology Fund. One of our primary collaborators is in FFRDC, a federally funded research and development center, MIT Lincoln Laboratory, which is primarily a DoD center. If you're interested, we have literally 50 technical papers, which are accessible via our website, or you can just look us up on ResearchGate. You can, I think we have 440 papers. Most of those are cosmology papers. There's a large paper called A Roadmap to Interstellar Flight, which will outline the technology I'm going to discuss. We now have stimulated and have funded 6 phase 1 and phase 2 programs, which look at various aspects of the technology, science, and applications. Where are we today? Where are we?
We're right here at NASA Ames.
NASA Ames, that's great. That was a great answer. Okay, thank you. Okay, I'll give you an A for that. Where's NASA Ames located? Mountain View, excellent, okay. Larger? On Earth. Okay, not that large. It's in a valley called the Silicon Valley, okay. Why do they call it Silicon Valley? very, very relevant to this talk. Why do they call it Silicon Valley? Because it's associated with the semiconductor industry, which is largely built on silicon, correct? Right, so all of your smart devices or not so smart devices are built on silicon technology, which is semiconductors, which are lithographed onto silicon primarily. There are other semiconductors, but silicon is the primary one. Okay, so there'll be a point in my talk where I'll talk about a congressional desire that by the 100th anniversary of the Apollo landing, which was 1969 for those of you that might remember, 100 years plus 1969 puts it at 2069. How far away is 2069 from 2018, math nerds? 51 years, okay, excellent. All right, so the future is hard to predict, but the past is a little bit easier to think about. What was 51 years from today in the past? The year would have been 1968, right? So if you were living in the Bay Area, you might have been dropping acid, or maybe you're working on semiconductor devices, or maybe you were, going to high school and thinking about starting Apple computers, right? Things like that. Yeah, 1968. Some of you were alive then, most of you weren't. I could tell just by the looking at you. Okay, I was alive in 1968. I was in high school. Okay, let's think about propulsion in 1968, since this is a talk about propulsion and you live at NASA Ames. 1968 was what in the NASA program? In the Apollo era, it was just before we went where? Just before we landed on the moon. We were going out, we circled the moon, or just about to circle the moon. I can't quite remember it was close. I think we were circling the moon in 68. We landed a year later in 69. Okay, how did we get there? We got there on silicon? No. What did we get there on? We got there on hydrogen and oxygen, right? Yes? Largely, okay. And how do we rate engines those days? Do we have horsepower? Do we have, kilowatts? No, we had, pounds of thrust, or, meganewtons for people that might be on the metric side. But think this through, because this is very much related to the entire premise of this talk and the place you live in. In 1968, what was the metric of performance of the Saturn V rocket, which was hydrogen and oxygen based? It had an ISP of about, any rocket scientists here? I can ask that. Thank you. Very good. You okay?
7.5 million pounds of thrust.
Pardon?
7.5 million pounds of thrust.
Total? Or per? Okay.
Well, for the
Total, yeah. Vacuum or sea level? Now we're getting to it. All right, fine. All right, okay. Thank you very much. Okay. Yeah, okay. So, but it had an ISP, which is a specific impulse of 450. Okay, that was 1968. Okay, let's fast forward 51 years later to 2018. What's the current engine that NASA is working on, which will soon be operational? It's called the SLS, right? Space Launch System, yes? What's the ISP, or the metric of performance of the SLS, which also runs on hydrogen and oxygen? 450. So we made a lot of progress in 51 years, didn't we? Now let's go back to 1943, which we'll go back in a minute. 1943 was World War II. There were rockets in 1943. They were based on oxygen and alcohol, which we'll show you in a moment. What was the ISP of the rocket in 1943 had it been run on oxygen and hydrogen? 450. We haven't made any progress in chemical propulsion, and we never will, in terms of metric of performance. Why? Because it's on the periodic table and it's bond breaking, and we will talk about that in a moment. You live in Silicon Valley. In 1968, what was the status of semiconductor technology? Intel had just introduced their 32-bit processor, right? Wrong. Intel had just introduced what? Nothing. They were about to introduce their 4-bit processor, or close to, which would come a few years later. That was 1968, sorry, we're going to go back and forth. 51 years later, from 1968 till today, 1967, sorry. How have things evolved in the semiconductor industry in the Silicon Valley? Dramatically. The reason that you're all here, the reason that you have these wonderful freeway traffic jams, I used to live up here. It sucks now, by the way, okay? It's really bad. The reason that you have that is because of the exponential growth in the semiconductor industry, yes? And yet, in the propulsion industry, if they had called this Propulsion Valley or Chemical Valley, which they might, actually. There's a lot of chemicals here. Okay, but if they had called it that, what would be here?
Tents.
Groves, right? Orange groves, apple groves, cherry groves, and tents, yes? No one would want to live here. Why? Because propulsion hasn't gone anywhere, and it never will. Now, that's obviously a bit of an overstatement, but chemical propulsion is not an exponential technology. The reason you live here is because this valley is based on an exponential technology. This technology is an exponential technology, namely photonics, which, like electronics, is exponential in its growth, and it can be applied to propulsion. You now have the confluence of two technologies, one of which is technology that is exponentially growing, and the other is a technology which needs exponential growth, namely propulsion. That's the whole basis for this talk. Okay, now we can get back to the slides. This is a map on the sky, as though it were the Earth, but looking up at the sky, of the roughly 150 planetary systems, stellar systems, don't call me. Okay, Steve Jobs, well, actually from far beyond, complaining that I said something nasty about the Apple operating system. This is 150 stellar systems which are within 21 light years of the Earth. Okay? In those 21 light years, if you look at this map where the color code, the color corresponds to the temperature map is given here. 225 is a brown dwarf. This is a white dwarf. This is very hot. Okay, the sizes are inversely proportional to distance. So small ones are 20 light years, big ones are 40 light years, i.e. Alpha Centauri-like things. If you look at it, most of them are kind of orangish. Okay, they have colors around 3,000 Kelvin. And they're roughly isotropically distributed. It's not great statistics, but more or less isotropically distributed, which will actually influence, if we're going to go to them, how we might have launch scenarios for those. Okay. We now believe there are more planets than stars in the universe based on the Kepler mission, which is a mission looking at occultation of planets in front of stars. We now believe that there is greater than one planet per star. You probably can't see this, on average. We think actually for M-class stars, which are most of the stars that we have in our galaxy and probably in the universe, there's actually more than one planet on average per star. That means in the entire universe, there's approximately 1 mole of stars. So if someone asks you how many planets are there in the universe, you say 1 mole, right? That's kind of a cute number. Of course, we don't know it with much precision, but we think there are greater than 10 billion trillion planets in the universe. Is that a big number? Right? That's your salary if we're exponentially growing from 1967 to today in dollars. Is that your salary? No, because your salary doesn't exponentially grow. Well, some people does, but not for me. Okay. This is those 156 stellar systems. This is the distance in light years versus their number. Don't worry about that. This is the temperature distribution of the stars. So this is kind of interesting to look at. Look at the temperature, and look where most of the stars lie in temperature. This is temperature in Kelvin. Temperature of our sun is about 42? No. 6,000. Okay, temperature of our sun is about 5,700 degrees. Most of the stars in the 20 light years from the Earth are around 3,000 Kelvin. That's called an M-class star. They're cooler than our sun, and that's useful and interesting for us in terms of planetary formation. Also turns out to be extremely important in terms of laser communication from the star back to us. Okay, so what is the goal of this program, both the NASA and the Breakthrough program? Well, for NASA it's somewhat different, but for NASA it's to develop directed energy for high-speed applications, lots of high-speed applications. One of them is to enable relativistic flight. This is the only known technology, and I'll lead you through all the ones that we know about. This is the only one that we know about that can achieve relativistic flight, and we'll go through each of them. It also has a lot of applications for rapid interplanetary missions, for beamed energy, for ultra-high ISP ion engines, for beamed energy for lots of other applications, including sending power to spacecraft, taking them out of orbit, planetary defense, space debris mitigation, et cetera. I'll show you a little more dramatic form in just a moment that chemistry has not changed, not just in 80 years, but really in 1,000 years. Go back all the way to looking at bottle rockets. Look at the ISP of a bottle rocket, and while it's not 450, it's of order 100 or so. Okay, so chemistry and even nuclear engines, which I'll show you in a moment, cannot get you to relativistic speed, and I'll show you a very dramatic example of that in a moment. However, unlike chemistry-based propulsion, photonics, i.e. the production and manipulation of light, is an exponential technology. With a doubling time that's very close to the so-called Moore's law, which is just an observation, by the way, it's not a law, doubling time about 18 months. It doubles in performance, halves in price in an 18-month time scale. So 18 months is a year and a half, yes? So going back 50 years, how many years and a half are there? Well, 50 divided by 1.5 is what? Anyone do the math? Well, divided by. So 50 over 1.5 gives you how many doubling times? About 30, yes? Approximately 30, a little more than 30. Okay, 2 to the 30th power happens to be a billion, by the way, a little more than a billion. It's a gigabyte, if you want to think of it that way. So that means in 50 years, semiconductors, like photonics, in 50 years have increased their performance by a factor of a billion. That's just about right if you look at actually what's happened in those 50 years. Chemistry has done essentially nothing. Okay. Right. So in 2017, we came to the attention of the head of the Appropriations Committee for NASA, which was John Culberson, who's a Republican from Texas. And he read about our work. We never contacted him initially. We have since then. And said that he thought it'd be really cool if NASA would prepare for a trip to the nearest stellar system by the 100th anniversary of the Apollo landing. So that's 51 years hence. And that's actually about the right time scale. So I thought it was actually rather clever. I've met him 5 times now. He's a very interesting person. They quote our NASA work in the congressional mandate. Well, it's not really a mandate, it's a suggestion. We'll be careful here. All right, so why do you want to go anywhere? Why'd you come here? Right? Because you could get out doing work and you can come in, right? Yes? No. Okay. Why don't you just watch this on YouTube? Well, you would have if they had streamed it. You would have come. We already had that conversation. So the difference between remote sensing, which is what you do at your desk all day when you look at that thing you call the monitor, versus going somewhere is really just a matter of degree. Everything is remote sensing. You're remote sensing. You're sleepy. Yes. Okay, I know that. It's okay. I'm sleepy too. If I were you, I'd be asleep a long time ago, frankly. I lecture for a living. I don't fall asleep, but when I listen to other people, I'm out, totally. Right? I even snore sometimes. Okay, so why not think of everything in terms of remote sensing? You're remote sensing me right now. Yes, you are. Your eyes are seeing me, with a few nanosecond delay for the people up here, and maybe 100 nanosecond delay for the people in the back. But you're all remote sensing me. So why go anywhere? Why don't we just build a big telescope? And so you can play that game, and we do build big telescopes. But when you play the game, you realize that you have to build a really, really big telescope to get the equivalent resolution. So for example, if we had a 10 centimeter telescope, which is roughly the size of your hand, and we got it within 1 AU, the distance from here to our sun, away from a planet like Alpha Centauri or Proxima Centauri, it would require the equivalent of a 25-kilometer telescope at the Earth or on the moon or nearby in order to have the equivalent resolution. Well, what if we got within 0.1 AU? It would require a 250-kilometer telescope, and et cetera. So you kind of always lose. You'd rather be on Mars with a rover digging holes rather than build a gigantic telescope, yes? And that's what a lot of you do for a living here, is you build close-up remote sensing. It's all remote sensing. You never really touch anything. You just remote sense it. Even when you touch something, it's still remote sensing. Okay, here's a picture of what humanity has done in terms of speed as a function of mass. Here's mass from atomic particles. This is protons and electrons, proton, electron. This is speed in meters per second. This is speed divided by speed of light. Here's 1. That's the speed of light. We get within 1 meter per second of the speed of light with elementary particles. But when you invoke chemistry, which is out here, this is you, right? So you haven't eaten lunch yet, so you're somewhere around here. You'll be over here after you eat lunch, right? You only get to speeds at most, which are 1/10,000th of the speed of light, at most. And that's for, Voyager after, whatever, it's 40 years now, approximately. Okay, so we cannot go fast with chemistry. It's not possible, and I'll show you why it's not possible in a really dramatic way. When you run a simple analysis of building a really big rocket, so what's a really big rocket? SLS? No, I want to go bigger. I want to take a rocket, I want to use all the Earth and make a rocket, but I want to go bigger. I want to use the entire galaxy. No, I'm going to go bigger. I want to take the entire universe. Make a rocket out of the entire universe and have the payload be 1 proton. Just 1 proton. Okay, that must go really fast, right? It doesn't. It only goes about 170 times the exhaust speed of the rocket, which would mean if you took the entire universe mass and made a proton for the payload, you would get nowhere close to the speed of light. It's hopeless with chemistry. What about nuclear engines? If you've read some articles about Daedalus or Project Orion, which was kind of a bomb-driven approach, looked interesting, but when you run the math, you realize it's not feasible for getting to relativistic speeds, no matter what the fusion process is. And if you're interested, I have an article coming out which discusses this. Even if you take the best thermonuclear weapons today and you use them to propel yourself, you cannot get to relativistic speeds. So if you look at all of the fusion reactions, here's everything from DT down to proton-boron, you realize the best you can get out is about 1%, less than 1% of the energy comes out of a fusion reaction. Fusion is essentially hopeless for getting to relativistic speeds, no matter what the engine design is, because the fundamental physics prevent you from getting there in any reasonable time scale. Now, if you're willing to wait 100,000 years, you can use Voyager to get to the nearest star. But most of you are not employed for 100,000 years, at least not in your current job. Maybe afterwards you'll be employed. But okay, so important points for relativistic missions. Chemistry doesn't work. Ion engines don't work. Solar sails don't work. Nuclear engines of any kind, thermal fission or fusion don't work. There's only 2 possibilities if you look at known physics, is you got to get to exhaust speeds which are close to the speed of light to have any hope of getting up to relativistic speeds in a reasonable time. And there's only 2 candidates, antimatter, matter, annihilation engines, and the other is using light itself or directed energy. Okay? So here's 75 years of propulsion and computing. Here's the V2, 1943. Here's the SLS, 2018. ISP, as we mentioned, hasn't changed. Here's a 1943 computer. The ENIAC was 500 flops. Anyone know what a flop is? Floating point operations per second. It was about 500 of them. Here's an Intel 2017 i9, which is about a teraflop, or 1 trillion floating point operations per second. This hasn't changed. This is not an exponential technology. In fact, it's flat. This is an exponential technology. It would be neat if propulsion were like this. Yes? Your lives would be a lot more interesting. Well, photonics is that exponential technology which can be applied to propulsion. Here's power. So think of this as flops, but for photonics, this is power of a single mode fiber as a function of year, and it has a doubling time of about 20 months, approximately. Here's the price in normalized 2016 dollars for a particular type of amplifier that I will talk about in a bit. It's dropping exponentially. So just like electronics, photonics grows exponentially in performance, drops exponentially in price. So what would we call this valley if we're not a semiconductor valley, but if it were a photonics valley? I'm just making this all up. I didn't intend to think of this, but someone think of something. We need a name. Light Valley. Light Valley. See, that's great. Light Valley is great, yes? Light Valley. Okay, I like it. We'll name something that. Okay, that's probably not. Well, one way to find engine efficiency for those of you that might be rocket scientists, which is not how this is not how you do it, but one way that's interesting to think about is take the kinetic energy of the exhaust and divide it by the rest mass energy of the exhaust. That's a metric of performance. We call that efficiency in our papers. The efficiency of light is unity, effectively. The efficiency of chemistry is 10 to the minus 10. So 1/10 billionth is what we're dealing with now. And this in our papers if you're interested. That one's not. If you're interested, read our papers for the physics of it. Basically, the speed that you can get a spacecraft when you illuminate it with light, because light has momentum as well as energy, you basically push it with light. The speed goes like the square root of the power that you have, the diameter of the optical system you use to illuminate it with. Some factors have to do with the reflectivity of the mirror that you're using on the spacecraft, and divided by the wavelength, that'll have the 1/2 power. And then it depends on the mass in this kind of funny way for an optimized system. Depends on the thickness of the reflector H, the density of the reflector, and then the mass of the spacecraft, all that to the -1/4 power, which means that the speed is a function of the mass, but in a very mild scaling relationship. We'll come to that in a bit. Okay, suppose we could build the system that I'm going to talk about in a moment, and you wanted to go to Mars, and you wanted to send a package to Mars. Let's say Amazon were here. Let's say Jeff was here, okay? And we said to Jeff, Jeff, how would you like to be able to send overnight, actually forget that, same day to Mars, okay? Like you could order sneakers and get them there the same day. That'd be awesome, yes? Or maybe you need boots or something, I don't know. Whatever you're going to need on Mars. So for photonics, which is the blue line, this is the trip time in days to Mars as a function of the payload mass. This is 1 kilogram. That's 10 million kilograms, okay, or 10,000 tons. The speed, the time to get there depends on the mass. Whereas for conventional propulsion, this is this engine here, the yellow one is approximately that of what we would send to Mars at the moment, and this is an ion engine. That doesn't depend on, this time doesn't depend on the mass because the speed doesn't depend on the mass. Just you build a bigger engine. So to get a kilogram to Mars with the kind of systems we're contemplating takes 8 hours, including stopping, which is, you do pay extra for that, but it's kind of important for most packages. Whereas it decays or gets worse as you go to heavier masses, but still quite amazing even with quite heavy masses. 10 to the 4th, or 10 tons, is the Orion capsule, or it's also similar to the Dragon capsule. Okay, how would you do such a thing? So how would you build a light source that were powerful enough to push a spacecraft? So the question is really not a question of power, it's a question of parallelization. So power can be achieved in a couple ways. You could build a 50 petahertz processor, or you could take 1 million processors that are a gigahertz and get the same performance. So how are supercomputers done today? Does anyone know where a supercomputer is? What's the closest supercomputer? Let me guess. Oh, you got one here. Right, okay. Okay, what's in that supercomputer? Let me get some CS nerd here.
It's like 150,000 chipsets.
Ah, awesome. Okay, you are going to get the Nerd of the Day award. Okay, yes, right. So supercomputers are made by what? Taking a lot of relatively mundane processors, i.e. multi-gigahertz now, processors, sometimes they use GPUs, and they gang them together in parallel, yes? Okay, and they're pushing towards 1 million now, right? They're up to hundreds of thousands in kind of current generation, but they're getting to 1 million. All right, and it's a parallelization problem, right? No one's building a 50 petahertz, or 50 peta is 10 to the 15, petahertz processor. You don't do it that way. You put them in parallel. That's the same way we would build this device. We would take a lot of relatively modest laser amplifiers, which you can think of as a laser if you will, but it's a laser amplifier, and we're going to put them in parallel. We're not going to build a multi-gigawatt single laser element. We're going to build lots of probably between 10 watts and a kilowatt laser amplifiers. And that's already been done long ago in terms of power. We build them in our lab now. Our students build them. They're tricky, but not so bad. The same technology that you use for going forward, you take one little laser here, which is really maybe a watt. You split it into a bunch of sub-elements. You amplify it. You phase control it. You then eject it. The light's added in free space. There is no upper limit to this technology. So you could build the, come on, you want to build a really big laser? You want to build the Star Wars nerds, come on. You want to build the Death Star, yes? How big was the Death Star? Any real nerds here? 900 kilometers, okay. So we don't want to go there, but if we did, it turns out we could do all kinds of cool things. So we're content with about 1 to 10 kilometers. But there is no upper limit to this. You power add in free space. The only upper limit actually is a flux limit when you tear the vacuum apart. It's not a power limit, it's a flux limit. If you run this thing in reverse, you would have a telescope which is electronically phase controlled. So this is a path forward, conceivably, to extremely large telescopes, kilometer plus scale. This would be really interesting for lots of other things, such as possibly imaging exoplanets or all kinds of other things in cosmology. Don't have time to talk about it, but okay, so if we're going to get to the stars, this is the only way at the moment that I know how to do it is using light to get there. Why don't we use antimatter to get there? Because I did say antimatter was an option. Who would like a kilogram of antimatter? Oh, come on. Oh, come on. Yes? I know you would. Okay, great. Someone's honest. I would love it, because I would take a gram, go out in the desert, and blow stuff up. Okay? If you want to know for reference, the largest thermonuclear weapon ever detonated was the Soviet Tsar Bomba, which was derated from 100 megatons to 50 megatons at the last moment, by the way. If you read the history of it, it's really quite interesting. That was roughly the equivalent of 1 kilogram of matter annihilated. 1 kilogram, that was 50 megatons. So I would love it, yeah, but you would not, okay? You would not like a world where antimatter was in abundance. Okay, but this kind of photonic drive, or using light to power spacecraft, because you don't carry the engine with you, the light source does not go with the spacecraft, it stays somewhere else, which leads to an issue of stopping, which we'll talk about later, is not just for little tiny things. So there is a kind of misperception that we only can use it for really small things. That's not true. We can use it for any mass, just more mass is slower. So this is speed in meters per second for various optical sizes. This is the array size. We call it an array because it's really an array of laser amplifiers, like an array of computational devices. This is in meters. This is speed. This is 10% the speed of light, 1% working on down. This is 10 to the minus 4, or 0.01% speed light. This is about where we get today with Voyager, with our chemistry. For a couple of different variants of the reflectors and the devices that we would use. But even for 100 kilograms, we can still, in theory, get to relativistic speeds. Okay, thank you. So it's not just for little things. Little things go really fast, though. Skip that. Okay, it's also very useful for interplanetary missions. As I mentioned, we could get to Mars in about an hour with a kilogram and get the moon in about 1 hour with a kilogram, if we master this technology. Okay, so what are we doing besides writing lots of papers and keeping people from, well, actually we help people go to sleep at night, because when they read our papers, they all go to sleep. We're actually starting to build stuff. So we actually have students gainfully employed in building directed energy systems. They kind of look like this. They look like a series of small telescopes, in this case lenses, fed by single mode fibers, driven by amplifiers. It's going to be a lot fancier than this in the end, and it's, of course, going to be way bigger than this in the end. But this is a prototype. You can actually get through the atmosphere, by the way, pretty well. You get about 95% transmission at a ytterbium line transition, which is at 1.06 microns from a high altitude site. So ground-based operation is possible. We face a lot of adaptive optics issues, which you had a talk last week by Claire Max, who's one of the world's experts in adaptive optics. She'll tell you that's really hard, and she's right, it's really hard. But that's what we're working on. One of the really tricky mathematical problems in this is, how do you phase up all the sub-elements? How do you synchronize your supercomputer? Well, for a supercomputer, it's not so hard, but for this, it's pretty tough. So we have a whole cascaded phasing algorithm that we're going through, looking at how to do this. It works on paper. We haven't tried it yet, but this is one of the sort of very tricky parts of this program. The power, by the way, is not the hard part. It is the synchronization, which is the really hard part. So here's a laboratory test bed. I'm going to lead you through some of the things that we do at UCSB. We built a custom system just to test all kinds of things in the laboratory that allow us to test multi-kilometer arrays in our lab. We have a really big lab. No, we don't. Okay. So this is a 2-element phased array that we can test out to 25 kilometers. We've now achieved, which is actually much better than I had thought, we've achieved performance which is actually better than is necessary. So let me lead you through this. The thing to look at is the RMS waves. How many waves do you get when you're done building this 2-element interferometer? Well, it turns out with no device under test, i.e. no array length, you get about 3 angstroms of effective length difference. You only need, we're going to operate at a micron, so you only need 100 nanometers, which is lambda over 10. This is vastly better than you need. So one of the things that really worried me about the whole program when we came up with this is, could we do this? And the answer is, at least on the fiber side, these are done using fiber optics, looks like this is not going to be the problem that I worried about. Then you take multiple kilometer lengths, you start laying them out. So look at this one. This is 2 1.1 kilometer lengths of polarization maintaining fiber, relatively well balanced, which is how you'd build the system. We get to 9 angstroms. Now, we can already get to within the size of a single atom with this system. If we do another 10 orders of magnitude, we'll be detecting gravity waves, but that's a different problem. Okay, so this works vastly better than I thought it would be. Even 25 kilometers, we're at 33 nanometers, which is lambda over 30, and that's unbalanced. So this is not the problem. Power is not the problem. This is, you don't want to know about that. Okay, then we started building our own amplifiers. Got it. Thank you. So you start with a seed laser. You have all kinds of fancy photonics stuff in here. You pump a ytterbium-doped fiber. You try not to blow it up with an isolator. Then you go into more stuff, more amplification, out comes power. So we've now achieved more than 40% efficiency. That's electrical power in to photons out. Okay? We've achieved 42% wall plug efficiency and greater than 30 kilometers of coherence length. So in a sense, we've shown that the fibers are not the problem. We've shown that the amplifiers can be built and are not, quote, the problem. Really, then it becomes an economics question. Okay? And the efficiency is already close to unity. You can only go another factor of roughly 2 before you're at close to 100%. So you're not going to go exponentially in efficiency. What we need to do is go exponentially down in cost. So we're working with our electrical engineering group, particularly John Bowers is just a master at doing semiconductor-based photonics, i.e. building like the semiconductor industry does with electronics, building photonics on semiconductors. So this is actually, I think, the way into the future to drive the cost down, just like the way to high-performance computing at low cost was put things on a wafer. Same thing here. So this is one of John's group's 32-channel beam steering systems. This guy is just amazing. That's boring. Okay. Okay. Then we have a program looking at building miniature spacecraft. So again, this program is not all about miniature spacecraft, but a part of it is relevant to miniature spacecraft. Remember, small means really fast. And from all the math we've done, it looks like we could send miniature probes out and get data back and send them at relativistic speeds. So this is actually quite interesting. So we're building these now at UCSB. These hold the equivalent of about 1 trillion transistors with current nanofab fabrication technology. And within 10 years, they should hold about 1,000 times that capacity, which is more than enough. That's not the problem. There's a bunch of stuff that is really kind of a technical set of things to think about. If you're going really fast in space, you might think space is nothing, but that's not true. Space has stuff in it. Space has protons, electrons, photons, and a little bit of dust grains in it too. So if you're really interested, look in our papers. One interesting thing is what I would call driving through the rain. So the interstellar medium, which is the space between stars, has about 1 proton and 1 electron per cubic centimeter. When you plow through that at relativistic speeds, you end up in a beamline plowing into the front of your spacecraft effectively. Okay, and you also get, in addition to Bremsstrahlung, you get nuclear interactions. It's really a fascinating problem, which I won't bore you with, but we've gone through the math. You want to fly edge-on, So fly with your windshield at the very edge, kind of like in Star Trek, except they need a thinner one. Boring. You do get X-ray production too, because you effectively have a nanoamp per square centimeter on your leading edge, and it's similar to the X-ray production in a roughly dental X-ray, but at low current. So we've done things looking at X-ray shielding. That looks okay. And the radiation shielding looks okay too, by the way. Reflectors, we've done some really neat work on, reflectors that you need, strengths of materials. This is the ultimate strength of material divided by the density as a function. Well, this is related to the speed that you can get to. There's a relationship between the two that we've worked out. This is for Mylar, this line. These are for different array sizes. This is for Gorilla Glass here, high strength glass. And this is for a hypothetical graphene. It would be great if we had graphene, but you don't need graphene. Turns out that even things like glasses will get you to 20% the speed of light. So that's really quite fascinating that we're already in regimes where existing materials look like they will work. So here's a 500 nanometer polymer film that we tested in our lab. And this, anyone know what that is? Some of you definitely got to know it. Anybody snore in the room? Anyone use a breathing machine? Yes, come on, you do. This is a CPAP machine. So how much pressure is on one of these small spacecraft when it's fully illuminated by the highest power we're contemplating? About that of your breath. So if you hold your breath, that's about the pressure you're putting on the spacecraft. It's not very challenging. So this is blown up with a CPAP machine. Laser communications, we have a whole 50-page paper on that. Also, if you're interested and can't sleep, or maybe this one's 35 pages, whatever. You can look at it. Backgrounds, yes, and boring. Okay. Implications for other things. Suppose there's something else out in the universe that might be, maybe there's an Ames on, on Virgo, right? Suppose they had one of these things and you wanted to know, could you see it? And the answer's in another paper, right? We're just a paper mill. Got it, 5 minutes. Okay, the answer is that you can be seen across the entire universe, which is really a profoundly interesting concept. That with this technology, if you were sending it out into the universe, which we're going to do anyway if we launch these things, some of the light will leak around, it can be seen across the entire universe. Now, of course, it would have to end up on something. But a more interesting question is, suppose there was a civilization somewhere in our galaxy, of which there are approximately several hundred billion planets in our galaxy alone, and they wanted to figure out if anyone could see them. The answer is contained in that paper that I just mentioned, and the answer is that you have a 100% probability of detecting that civilization if they do nothing but what we call intelligent targeting, i.e. shoot their light at the stars which contain the planets, which in theory contain the life. That's a really interesting conclusion because all you need on the detection side is a very small telescope, roughly 10 centimeter in diameter, covering the sky. Anyway, if you're interested in that, take a look at it. Okay, then we get to, well, who's going? Maybe they want to do tourism on the moon or Mars, but guess what? People are high maintenance. You have some friends who are high maintenance? This is really bad, okay? People are bad. On the other hand, there are creatures out there which are much more interesting. So anyone watches Star Trek Discovery? Anybody see that? Yes? Okay, remember that? Yes? Okay, you get it. You're right. You're going to get the award of the day, right? There's tardigrades in there, yes? Yes, absolutely. So these guys can be put into sleep mode indefinitely. And they don't require anything. No metabolic support at all. Zero. Right? You're getting sleepy. Something over there. Okay, right? No metabolic support. They're rad hard. They're tiny. And I know they're not as good as your, significant other. Maybe they're better, I don't know. Because you can put in sleep. You can just say, go to sleep, okay? Off, you're off, okay? Some of you would like to do that with others. And C. elegans is another one. So we have a collaboration with our biology department to look at preparing life forms that would be suitable for interstellar travel. Highly controversial, not something that NASA and possibly other organizations want to do. It's really a societal decision. Our interest is to see, is it possible? Then society has to decide if they want to send out life. It's not something that we're going to do by ourselves. Where do you put such a thing? Well, I already said you could put it on the ground. So with Breakthrough, that's where we're going to start. We're going to put it on the ground. But eventually, this is an evolutionary approach. It's both revolutionary and evolutionary. You'd want to put it someplace, ideally, that's stable, doesn't have an atmosphere, ideally. And the moon is one of the logical places to do that. So we've done a lot of work on looking at the moon. The backside of the moon is nice because you can't point down the Earth, which some people might worry about. It doesn't keep me up at night, but I'm the one who wants a kilogram of antimatter, so why would it keep me up at night? Anyway, the moon's a great place to put this, and we have some things for the moon. So this is one hammer which gives you lots of applications, from large telescopes to laser comm to power beaming to high ISPI engines, which we have another NASA program on, planetary defense, asteroid detection. There's all kinds of things you can do with this. It's really an interesting technology. It's not a one-trick pony at all. It's something that we really need to do. You know why we need to do it? Because if we don't do it, someone else is going to do it. It's time to do it. Okay, system costs. We have actually an analytic cost model, which is really quite interesting. If you tell us how much money you have, we can tell you how fast you can go for a given set of assumptions about the cost per watt and cost per square meter. Okay, lots of challenges, yes. A lot of them are economic issues, interestingly enough, not so much technical issues, except for the phasing part. That's a big technical issue. How do you amortize such a system? You build one system, and then you launch an unlimited number of spacecraft. The spacecraft are cheap. The system's not cheap. So it's not like you're blowing your rocket up every time you launch it. Okay. Well, SpaceX kind of figured out that one, too. Okay, conclusions, right? This is a path forward to sort of revolutionizing propulsion for certain applications. We're not going to eliminate chemistry. That's not our goal. It's to point out that this is a truly transformational technology in areas where you require ultra-high speed, and it's the only way known forward to, I will end in a moment, to interstellar flight. And then you have all these other applications, from asteroid mining to asteroid deflection to ultra-long-range space comm, space debris mitigation, power beaming, et cetera. There's also some interesting laboratory applications, which I won't get into. This really does leverage Silicon Valley, but in a different way than you might imagine. We're not leveraging Silicon Valley in terms of electronics, but in similar ways with photonics. The next 5 years are really crucial, which we're grateful to the Breakthrough Foundation for their vision in seeing how incredibly this program could influence humanity. The next 5 years are critical to basic understandings of technology and beating down the tall poles. So one of the reasons why I'm here is we would love to get more collaboration set up, introduce you to the technology and see if you're interested. Lots of challenges ahead, and in my opinion, the United States should be the one to lead this transformation. It also happens to be a magnet for young people. So in the last several years, we've had more than 100 people, more than 100 students work in our lab on directed energy. They come to us and say, oh, we heard about this really cool program, and by the way, we love to blow holes through things. And there's some connection between the two. And here's my roommate's cell phone, could you please blow a hole through it, which has happened, by the way. So it's a great outreach program, and it really stimulates the imagination of lots of people, including the public. Okay, so I'll stop there and take questions. Thank you.
Thank you very much. So we have time for a few questions. If you have a question, please raise your hand. We'll have someone come with a mic. Stand, ask your question, one question, and then we'll move forward.
Just a quick question. In terms of slowing down, how do you manage slowing down using the directed energy from your launch site?
Yeah, it's a great question. So the question was, how do you slow down? So remember in the opening scene in Spaceballs? How many of you have seen Spaceballs? You've seen it, yes, okay. So we need someone else to answer. Remember the opening scene in Spaceballs? The ship's moving. Finally you see the bumper sticker and the license plate, and what does it say? Pardon? Yeah, we stop for nobody. Okay. So if you want to go to relativistic speeds, there's no known technology, with the exception of this technology, that can stop you. Well, that's not true. It's very easy to stop. You just planet, aim, stop. Okay, works really well. Unfortunately, a gram, going at the speeds we're talking about, is a kiloton of energy. A kilogram is a megaton. So you stop, unfortunately, you have some collateral damage to your spacecraft in the process. If you want to slow down gracefully, the only known technology is this technology. Well, we don't think there's going to be this technology at the other end to just slow us down. However, so these would be flyby missions for the small relativistic missions. But that's fine. All of our early spacecraft missions were flyby missions going out to outer planets and inner planets. However, if we're going to the moon, going to Mars, it's conceivable to build a system like this at the other end. The other option for near-term objects like the moon and Mars is you can use the light reflected off of a mirror on the other side to push back on you, either something that you prearrange there, so you don't really have to have another laser array. All you need is a reflecting element, or in theory you can eject something, but it doesn't really work out very well. So this technology in the direct photon drive mode is really designed primarily for flybys, except for nearby objects where you'd ping pong back and forth, which is actually something practical to think about. However, when you combine this with ion engines, which is what we're funded on another NASA program, is you cannot reach relativistic speeds, but you can drive much larger masses at slower speeds. So one of our targets now is looking at 100 to 200 kilometers per second in spacecraft driven with high ISP ion engines that are driven by beamed power. So we use the same system, same technology, but instead of just driving with photons, we reconvert to electricity and then drive an ion engine. There, you just flip it around, and you can stop or come into it. So I think for within our solar system, particularly outer planet solar system missions, the ion engines coupled to the beam power makes a lot of sense. If you want to send a CubeSat out really fast, let's say you wanted to get to Enceladus or someplace else, just to get out a probe, then you might want to send it out at by direct photon drive and not worry about stopping, which for many missions is fine. But it's a great question.
So first of all, thank you for the great talk. And I kind of understand how it works for the propulsion application, but how do you change it to do something like asteroid mining, like you mentioned, or asteroid detection? How does it differ in usage?
Yeah, so a lot of our early papers are on planetary defense, which is actually how the whole thing started. And then when we realized that NASA was not going to fund planetary defense, we started this in 2009 on looking at planetary defense. And immediately we realized, well, we can use this for propulsion. We started submitting proposals in 2013 to NASA on planetary defense. It was obvious, okay, NASA's not interested. No one's taking on that as a real goal. Now I know we have an Office of Planetary Defense, but it's more for detection. And there are impactors. So for diverting asteroids and comets, we have about 20 papers on this now. What you do is you ablate the surface, and in the ablation process, you're basically producing an engine, a rocket engine. So we've done the lab tests on this. We have videos on our website. If you go to our website, just look us up, you'll find it. You take the light, heat the surface, it blows out material, that forms a rocket engine that then diverts the asteroid. Turns out to be quite effective. It's actually, you get more thrust per unit power than an ion engine, which is not unreasonable when you go through the basic physics of it. It's actually comparable to a chemical engine. Okay, and it can be similarly used for mining in different ways. Okay, yes?
Excellent talk. A couple questions. One, does the amount of power that your laser beam or energy that your laser beam can impart on the satellite decrease as your satellite gets further away from the source? And also, if you had a laser on board your satellite, could you fire that laser, say solar or nuclear power, to generate thrust in an arbitrary direction?
Yeah, okay, so two great questions. So there's a couple of effects. One's a somewhat subtle effect. As the spacecraft gains speed, there's a Doppler shift that goes on. So you do have a slight decrease in thrust from relativistic effects. That's a relatively small effect. As the spacecraft gets really far away, the ability to put the spot onto the spacecraft is no longer sufficient to keep the beam within the spacecraft reflector. And in our case, there was a reflector and a spacecraft. They could be thought of as two separate things or one, doesn't matter. But eventually you diffract enough that part of the beam overspills the spacecraft, and then yes, the power is reduced at that point. The calculations take those effects into account, both the relativistic and the overspilling effect. And the one thing I forgot to mention, I don't want to leave you without this. For the small spacecraft, the time it takes that the laser's on is not the time it takes to get to the target. It only takes about 100 to 200 seconds to accelerate up to roughly 20 to 30% speed of light, and then you're ready for the next mission. So you could launch missions every couple of minutes if you wanted for small spacecraft. Large spacecraft, you have to illuminate longer. Okay. In terms of putting a photon source on board, a laser on board, the problem is when you go through the details, it doesn't work because all the mass required to take the infrastructure to have that on board is enormous compared to the mass that you want to send out. So that unfortunately does not work. If you had antimatter on board, that would work, but if you had antimatter, you'd probably use that for propulsion. So unfortunately, you're stuck just by the basic physics of the problem. Okay. So if you compare this to a fusion engine, which people are interested in using fusion as a propulsion system, fusion works okay up to, say, 50 to 100 kilometers per second, but you cannot get to relativistic speeds in any way with fusion. But I think that one should look at the landscape here in different ways. What is the mission space you want to achieve? If your mission space is going relativistic to go interstellar, this is the only game in town with the exception of antimatter. If you want to go and look at high-speed planetary applications, then you have a couple of choices. You can use this technology by itself, driving directly with photon drive. You can use this technology driving ion engines, which we have this other NASA program for. Or you could look at fusion engines and be content with lower speeds. The issue, there's a scaling difference between the two, which is critical. Fusion engines do not scale well to low mass at all. First of all, we have no fusion engines, okay? But our thought is that you're going to need large engines for any fusion device. Even thermonuclear weapons don't scale to the firecracker size. Okay, you have to have a certain critical size. So fusion engines are not going to work for, say, CubeSats, whereas this can work for any mass from tiny to large. So I think one should look at the parameter space of not either or. It's not like you want to displace chemistry or not pursue nuclear ideas, but this opens up a huge parameter space of possibilities. Okay. But good questions.
So I was curious, can you use this to launch off of planetary objects, or do you have to have it like launch into space with conventional
No, you can
methods?
launch. Okay. You can launch directly. So the picture I showed you of the moon was a good example. I know these went really fast through these. The idea in the moon is you would launch directly off the surface. So you basically levitate. You can even do it on the Earth, by the way. It's just more complex. We have a paper on that coming up. You can launch off the surface, and then you can accelerate. What you don't want to do is go really fast off the surface that has an atmosphere. The moon, since it has no significant atmosphere, that's not a problem. But yes, the issue is how much mass can you send off the surface? And that's really just a very simple calculation. You get about 6.6 nanonewtons per watt. So when you work out the math, we can launch off the surface using the rays we're talking about, of order 100 kilograms or so, a little bit less than that, directly with no other assist. One possible hybrid mode is to use an ablation engine, which then gets you off the surface with higher thrust per unit power, but is not capable of high speed. And then once you get out, then you get away from the gravity well, and then you accelerate out. So there's some interesting hybrid approaches. In the Breakthrough Foundation work, we assume that we launch it's kind of a mothership of small spacecrafts that are available for launch. And then we kind of have like a cassette ejector, eject it, and then we hit it with the high power beam to launch out. But there are these other approaches too. Okay.
So please join me in thanking Dr. Phil Lubin for an excellent talk. Very good.